Okay, we'll next go to Ashley. So Ashley is here at Stanford in the Stanford Student Space Initiative.
I want you to look at these 3 space missions. What do they all have in common? Well, they all have satellites in them, and they're also all rendezvous missions, or they have some form of a satellite swarm. Something that's super interesting about this is the advent of CubeSats. CubeSats are basically little boxes of technology that we have been able to send to space for much cheaper, with the new transporter missions from SpaceX, which you may be familiar with, and other transporter missions hosted by new and running companies. So what I'll be talking to you about today is traversing the data desert and pioneering low-cost CubeSats, or essentially, how can we run a space mission for dirt cheap? So first, I want to bring you through my mission of working with the satellites team at the Stanford Space Initiative. I've been a co-lead at the Stanford Space Initiative of the satellites team, and it's really amazing to see what you could get done in just about a year or a year and a half. In fact, we were able to launch a satellite into space last year, which was super exciting, and you can actually see it taking off on a Falcon 9 rocket in the top right photo. I even had the opportunity to take a long exposure of the Falcon 9 rocket, which was super fun since I love photography. So I want to take you through my journey. First, I want to mention that the name of the satellite was Magnifica, which we launched last winter. And I'm going to be talking more so about Samwise, which is our satellite anticipated for about October of next year. This is very exciting since it has double the space and so double the amount of technology, essentially. And the coolest part about it is to mention a couple of features. You could even see deployable solar panels on the left and right sides. And I'll be specifically diving into a navigation payload today. So the first thing I want to do is reflect on what data did we even get from Magnifica, and how could we maybe use this for Samwise? And then I'm going to be talking about some work I had gone to do with the Space Rendezvous Laboratory with Simone D'Amico on campus. And then I'll be talking about testing campaigns and if we really need the expensive equipment that majority of space companies have. And then lastly, I'll talk about thinking of Samwise and how we could leverage these data-driven methods to make our satellites even better. So to give you a little bit of background on how our team operates, we do everything in-house. Everything down to designing the circuits, designing the CADs, designing the software for communication and everything. You could even see me placing a PCB with tweezers, which we use as our flight computer. I would say the most important fact to recognize about this is that you can only trust your data so much, because we did it all. And so I want to talk about how we can create methods to better analyze the health of our satellite, even though we may be uncertain about a million other things. So first, I want to mention that the only time we can communicate with our satellite is when it's directly overhead. And so we can only talk to our satellite once when it passes over Stanford's ground station. And these orbits are only about 90 minutes at a time. And so we only have these lapses of about 10 to 15 minutes when we can have a clear communication with it. So the first thing that we had done about this is set up our satellite on a network of tiny ground stations called TinyGS. This is a network of amateur radio operators who are able to collect information such as IMU data or battery voltage and so forth. This allows for us to create graphs like the one on the right of our battery health or the battery voltage to see if it's charging right or discharging correctly. This is at the courtesy of one of my teammates who made this amazing graph. So you may be realizing that most of the information we need is actually normally not available. So what can we do about this? What else can we do? Something really important to recognize is the value of simulations, or simply just using physics models. This is a data-driven approach that allows for us to be able to analyze the orbits, which we normally don't know about 80% of the time. In fact, when our satellite's in space, it's very difficult to know where it's at, as Sam mentioned in her presentation about starfish. So what I had done at the Space Rendezvous Laboratory is worked on a separate mission where I learned how to model orbits, such as around the moon in this scenario for a near rectilinear halo orbit. And the most interesting part about this is you could actually take sample patches of the sky that you would anticipate at each given point in this orbit. And so this allows for you to leverage navigation technologies and learn how they may operate at different points in your anticipated orbit. As an example, on Samwise, our upcoming mission, I've been specializing in working on the star tracker. The star tracker essentially takes a photo of the night sky when it's in space, and then it takes all the stars out of that image, pinpoints them, and then uses them as methods for figuring out where the satellite's pointing and what the attitude is. It's basically like a pirate in a sea, and it's lost out there. And so what we could do about this is actually come up with quantitative diagrams of how our software is performing when you make certain changes to it. As an example, in the Space Rendezvous Laboratory, I focused on a rendezvous mission between 4 CubeSats. This was just an example to gain more experience with learning how to simulate the data necessary to test our own satellite. In this scenario, you can see on the left-hand side, when not including additional data such as the distance between the satellites, that you would obtain higher errors. And so the shaded region is actually able to shrink a lot in comparison to when you don't have those kinds of features available. We simply would not know this if we didn't go out of our way to test it in the first place. In fact, we were able to obtain, although not pictured here, around 450 meters decrease in error in the longitudinal direction, which is super exciting. Another topic I want to talk about is simply taking your camera and just going outside and trying it yourself. We use a Raspberry Pi camera on our satellite. And so what we had done, or what I had done, is went out to Wilbur Field, set it in the grass, which you may have walked through, and just took about 50 or 100 photos. Something very exciting about this is you can go ahead and run your star tracker algorithm, although with a little bit of noise and light pollution, and see how it performs. What I had done is I applied Viner 2, a library from MATLAB, and a series of other filtering techniques to try and obtain a better image. Because the Raspberry Pi camera is so low quality, you may see a lot of noise and a lot of distortion in the photo, except we could definitely do things to mitigate this. It's very important that you recognize the value in simply being able to go outside and for free take photos rather than having to focus on millions of dollars or billions of dollars of equipment normally required for big space industry missions. So you can see here how you could go from an image that appears practically completely black to an image where you can go ahead and pinpoint example stars. This is very interesting because it allows for us to think of how we could improve the star tracker and also how we could get more universities able to work on these software missions. The most important fact about this is we're currently making efforts to be able to open source every part of our software. So down to the CAD files and the circuit files and the code that I'm writing right now for the star tracker, that should all be completely accessible to any university team that is seeking to build their own satellite. So I want you to come to the conclusion that we never really have enough data, but we can get remarkably close. And so whether this means you go ahead and reflect on past missions if applicable, or whether you try and simulate the data yourself, or whether you simply go outside and you try to gather the data by just taking some photos outside. Those are all methods for trying to test your algorithm in a low-cost manner, and I'm very excited to see where Samwise goes about 1 year from now. Thank you.